In today's lesson, we want to look at division of polynomials. Before we get into how division of polynomials will work, we want to look at just long division in general. So let's say, for instance, you want to take the number 2 and we want to divide that into 433. Well, if you take 2 divided by 433 using long division, what do? Well, you first ask, okay, how many times does 2 go into 4? Well, 2 goes into 4 evenly twice. 2 times 2 is 4, and then we subtract. 4 minus 4 is 0. Now we then ask, how many times does 2 go into 0? 2 does not divide into 0, so therefore we have to drop number down, in which case that's a 3. And now we can ask, how many times does 2 go into 3 evenly, in which case it's 1. 2 times 1 is 2, and once again we can subtract and get 1. Now here we ask the same question, how many times does 2 go into 1? It does not divide into 1, therefore we have to drop down the next number here, the 3. Now we ask the question again, how many times does 2 go into 13 evenly, in which case we say 6. 2 times 6 is 12, and we end up with 1. To remind you here, we would have 433 is going to equal my divisor times my quotient plus my remainder. Now we will extend this idea to polynomials, where our polynomial will equal our divisor times the quotient plus your remainder. Notice here one property is your remainder must always be less than your divisor. As if my remainder was greater, we would continue our long division process. Let's take a look at the exact same method of long division for polynomials. So in this example here, we want to divide x squared plus 3x minus 1 into x to the power of 4 minus 81. So using long division, we want to ask ourselves, what can I put here such that I get an x to the power of 4 here when I distribute this and multiply? Well, if I were to put an x squared here, we end up getting x squared times x squared is x to the power of 4. And then continuing that distribution, you have x squared times 3x will give us positive 3x cubed. And then x squared times negative 1 is negative x squared. We now want to subtract these together. You can view x to the power of 4 minus 81 with its coefficients that aren't present. So by that I mean we could write down x to the 4th plus 0x cubed plus 0x squared plus 0x minus 81 if you wish. And, as you work through this and get more practice, you don't actually have to put these in here, but sometimes, definitely the first couple of times, it is helpful. So in this case here, we want to take x squared minus x squared is 0. 0x cubed minus 3x cubed is negative 3x cubed. Continuing on, we have 0x squared minus negative x squared becomes positive x squared. Then we have here 0x minus, again, there should be a 0x here, so we don't have to write anything down. And then lastly, negative 81 minus no coefficient will leave us with negative 81. We then move on to our next placeholder, and we want to know what goes here, such that when I distribute that over and multiply, I'm going to get here negative 3x cubed. Well, I already have an x squared here, so if I put in a minus 3x, you'll notice that minus 3x times x squared will give us our negative 3x cubed. So distributing that, we get minus 3x cubed, and continuing on here, minus 3x times positive 3x is minus 9x squared, and again, minus 3x times negative 1 is positive 3x. And again, we're going to go ahead and subtract. And once again here, these will cancel. Then we have x squared minus negative 9x squared is going to give us 10x squared. And then we have here, again, I don't have an x up here, so it's going to be 0x minus 3x is negative 3x. And then lastly, negative 81 once again. Continuing on here, following the same idea, we're going to put a plus 10 here, in which case doing multiplication, we get 10x squared plus 30x minus 10. And subtracting this time, we get minus 33x minus 71. So putting this all together, we now have our quotient, our divisor, and our remainder. We can now express x to the power of 4 minus 81 as a product of the divisor and quotient plus our remainder. Let's do that now. And you'll notice here we now have x to the power of 4 minus 81 is going to equal our quotient times our divisor plus our remainder. This is known as the division algorithm. Notice here that our remainder, the degree of our remainder here is 1, and notice the degree of our divisor is 2. It will always be the case that if done properly, the degree of your remainder must be strictly less than the degree of your divisor. Because if the degree of the divisor and remainder were the same, you could continue the long division process and decrease your degree of your remainder. Let's take a look at generalizing the division algorithm. So summarizing our division algorithm here, we have let p at x, q at x, d at x, and r at x be polynomials. Let p at x be a polynomial divided by some divisor, d at x. Then the polynomial will break up in the following fashion, where our polynomial p at x is equal to the product of its quotient times its divisor plus its remainder here. And again here, take special note that the degree of your remainder must be strictly less than the degree of your divisor. Let's take a look at some questions. In this next example here, we want to take a fifth degree polynomial and divide it by x squared minus x plus 1. Let's take a look. Well, first term we're going to put here is I need to get a 5x to the power of 5 here. So by putting here a 5x to the power of 3, you'll notice 5x to the power of 3 times x squared gives us 5x to the power of 5. Continuing on, we have minus 5x to the power of 4 plus 5x cubed. Subtracting, we get 5x to the power of 4 minus 3x to the power of 3 minus 3. Continuing on here, we get 5x squared will be the term that does it. And again, distributing that into this polynomial here, we have this expression. Subtracting, we get 2x cubed minus 5x squared minus 3. In this place here, we need to get a 2x cubed. So we will put in a positive 2x. Distributing, we get, and subtracting, we get. Lastly here, putting down a minus 3 gives us, and subtracting, we end up getting a remainder of negative 5x. By the division algorithm, we have our polynomial is equal to our divisor times our quotient plus our remainder. And notice here the degree of our remainder is 1 and the degree of our divisor was 2. So that relates to our previous discussion where we discussed that the degree of your remainder must always be less than the degree of your divisor. Let's take a look at another problem. In this question here, we want to take x cubed minus 8 and divide that by x minus 2. Notice here we already know how this breaks up, right? If you use your difference of cubes formula, we know that x cubed minus 8 is equal to x cubed minus 2 cubed. And using our difference of cubes formula, we get x minus 2 times x squared plus 2x plus 4. Now we can go ahead and take a look at this using long division, and we should get the same results using our division algorithm. So in this case here, we have x minus 2 divided into x cubed minus 8. Well, we're going to put an x squared here. Distributing, we get x cubed minus 2x squared. Subtracting, that gives us 2x squared minus 8. Going to have to put a plus 2x here, in which case we get 2x squared minus 4x. Again, subtracting, this gives us 4x minus 8. And now here we're going to have to put a plus 4, which gives us 4x minus 8. And you'll notice here your remainder is 0. And notice here using our division algorithm here, we have our x cubed minus 8 is going to equal our divisor times our quotient plus our remainder. Remainder is 0. And we get exactly the same result we got when we were using difference of cubes formula. All right, let's take a look at another example. In this last example here, I want to show you that you can use long division to divide out not just polynomials, but also multivariable functions. Let's take a look here. I want to prove the following result. X cubed minus y cubed is equal to x minus y, x squared plus xy plus y squared. So essentially the difference of cubes formula. How can we prove this using long division? Well, let's take a look and see what happens if I take x minus y and divide that into x cubed minus y cubed. Well, going through the same process here, I'm going to put an x squared here so that I can get an x cubed in this location. Distributing, we get x cubed minus x squared y. Subtracting here, the x cubes will cancel, and we'll be left with x squared y minus y cubed. Now, I want to get an x squared y in this position here. Well, therefore, I'm going to have to add an xy. So that when I distribute this xy into here, we get exactly x squared y minus xy squared. And again, subtracting, these x squared y's will cancel, and we'll be left with xy squared minus y cubed. And now again, I want to get an xy squared here. Well, I already got the x. That means I just have to put a y squared here. Distributing, we get xy squared minus y cubed, and subtracting, we actually get a remainder of 0. So notice again, using the division algorithm, we get x cubed minus y cubed is equal to your divisor times your quotient plus your remainder of 0. And again, we unravel and prove the difference of cubes formula using long division. Okay, that concludes today's lesson. Just a quick introduction to long division of polynomials. And in this example here, you're seeing it extends to multivariable functions. Feel free to review these and take a look at my next lessons further developing this concept. Thank you.